Good day. So now we're going to do unit 1.2, which is about chemical reactivity of gases. So if you look at your periodic table here, you haven't read the elements that are in the gas form at room temperature. So we have hydrogen, nitrogen, oxygen, fluorine, and chlorine that you know of, and all the noble gases as well. So how do we know if something is reactive or not? If you remember from last year, this has everything to do with the valence electrons. And you can know how many valence electrons a substance has if you look at the group number on top. So this one, for example, has 5, 6, 7, and 8 over here. And if I may refresh your memory, if something has 8 valence electrons, it is stable. It does not want to react anymore. That's why we call these inert gases, because they are inert, they do not react. It's a synonym. So, chemical reactivity is based on valence, but also the type and the strength of the bonds between the atoms. For example, if in a molecule we have single bonds, those are not as strong as double or triple bonds. It takes much more energy to break double and triple bonds, which means those molecules will not be as reactive. So the classification here is based on that. And based on that classification, and because we can predict how certain atoms can react, we again can come up with different uses for those gases. An example, something typical, noble gases. They can create colored light when they're subjected to electricity. Again, if we give them energy, the atoms get excited, their electrons gain energy, they will leave the atom because they have that surplus, they get very excited. And when they leave the atom, well, they don't like to be in that excited state, so they will come back to the atom, but will release that extra energy in the form of a photon, which we see as colored light. So again, that's an example of the quantum theory. Another type of use that we do based on characteristic properties is with hydrocarbons. So hydro for hydrogen, carbon for carbon, obviously. So all the compounds that are formed of carbon and hydrogen in different amounts, different ratios, all have similar properties. So we have CH4 methane, for example, C3H8 propane, C4H10 butane. So all of them we can use to do combustion, for combustion. So if we look at why certain elements react faster than others, such as chlorine and argon, we have to look again at their valence electrons. So if we go back to the previous page where we have the periodic table, we'll look at chlorine. And chlorine is number 17, so we're going to draw it. So if you recall, when we want to draw an atom, so if it's number 17, so I'll just, oops, sorry about that. Let me get a pen, let's take blue. So this one has the nucleus with the 17 protons. If we just look here, sorry, it has 3 shells because it's on the 3rd row. So we will separate the electrons on 3 shells. So I'm going to have 2, 8 for a total of 10 and 7 on the last one. Chlorine is indeed in group 7, so it has 7 valence electrons. If we go to argon, let's verify. Argon is over here, so it has 18. So let's draw argon. Okay, so let's pretend we have the nucleus over here. So again, it has 3 shells with 2, 8, and 8. So back to my question. Why are halogens more reactive than noble gases? So chlorine is my example for halogens, and argon is my example for noble gases. So chlorine has 7 valence electrons. It needs to gain 1 more to become stable. It's so close to stability that it will react very quickly. It will try to grab that 1 electron it's missing, and that it should achieve that extremely quickly, so making it very reactive. As opposed to argon, already has 8 on the last shell. It's already happy, it's stable, so it will not react. And that's how we compare how one element is more reactive than the other. Again, it's based on the valence electrons. The closer an atom is to achieving stability, to being close to, or to achieving that octet rule, right, that those 8 electrons on the last shell, the faster it will react. If an atom, for example, were to lose 3 electrons versus this one that needs to gain 1 only, this one will be more reactive than the atom that needs to lose 3, because it takes longer to lose 3 than to gain 1, for example. So that's it for reactivity. Now, we have here an image that shows you different flames from 4 different Bunsen burners. And the question is, why are the flames of different color? Well, typically when we burn hydrocarbons, they will release a yellowish color. If you think about a bonfire, that's what you see. You see a yellow color. The flame is yellower. Now, why is this one blue? If you think about a Bunsen burner, you know that the neck of the Bunsen burner can be turned, and that allows for more or less oxygen to be used in the combustion. The more oxygen you use, the more complete that combustion will be, meaning that there will not be any residue of that substance you're trying to burn. So it will give you a blue color. All that you have left, if you remember what a combustion produces carbon dioxide and water vapor, which we perceive as blue, right? If you think about a lake or an ocean, we often, even as kids, color that in blue. There's a reason for it. Water reflects, when it reflects the sky, looks blue. So water is seen as blue, and that's all we have here. 100% of carbon dioxide and water vapor, which means there's no residue of the fuel. Everything got burnt. This one here is an inefficient combustion. So we have a lot of the fuel that is still left unburnt because there weren't enough oxygen to burn all the fuel. So that fuel shows a yellowish color. And we have the two in between where we have a little bit more oxygen, so a better, more efficient reaction. Again, a little bit more efficient if there's even more oxygen, and 100% combustion of the fuel if we have enough oxygen. So that's why the colors are different. It depends on how efficient that combustion is, and that is based on how much oxygen is being supplied to the reaction. Okay, so that's what we have here under the box. That leads us to different types of combustible gases and what do we need to have a combustion. So combustion is a type of oxidation. Oxidation, if you remember from last year, that means that oxygen is involved, O2. Combustion is exothermic, it releases energy. And we need 3 things to have a combustion. That's why we call it the fire triangle. The first one is oxygen. Oxygen could be changed or could be replaced, I should say, by ozone or by a halogen. It will do the same job, but 99% of the time combustion will use oxygen. We need heat to start the reaction. It's not because you stare at a piece of wood that's going to catch on fire. You need to use a match to actually start your fire. So you need to supply a certain amount of energy to kind of jumpstart the combustion. And lastly, you need a fuel. You need something to burn. And that can be a solid, a liquid, or a gas, but typically we always think either solid, if we think of wood, for example, or if we think of propane, methane, and company, then you'd have examples of gases. Alcohol would be an example of a liquid. Now, obviously, since we need those 3 things, if you remove one side, if you have no fuel, or if you don't supply enough heat to start the reaction, or if you don't have any oxygen present, then you cannot have combustion. And that is why when you try to extinguish a fire, you'll try to cut off the oxygen supply by using, for example, a blanket. You'll try to cover and smother the fire. So you're cutting off the oxygen supply, you're removing one side of the triangle, and the combustion stops. You probably remember from last year that combustion produces carbon dioxide and water, and sometimes, depending on the fuel being burnt, some residues. An explosion is a type of very fast combustion, so which means that there's high reactivity there. So it is a combustion, it's just that it happens so quickly that it releases all the energy at once, thus creating an explosion. Hydrocarbons, I talked about it before, so it's those are compounds made of carbon and hydrogen. So again, you have examples here. These, because they're only made of carbon and hydrogen and nothing else, will only release carbon dioxide and water, no other residue. And again, your energy, because it's an exothermic reaction. Hydrogen, why do we call it clean fuel? Well, it's because your product is water. There's no carbon dioxide being produced, and therefore you don't create greenhouse gases. So that's why we call it clean. Finally, we have oxidizing gases. So again, oxygen, the most prevalent, the most common one. Obviously, the more you have, the faster the combustion. It's like saying the more workers I have to build a house, well, the faster I'm going to build the house, right? So it's the same thing here. O3, ozone, can replace oxygen. One point that should be made is that ozone at low altitude, so in the troposphere where we are right now, that can be toxic, and that actually causes smog. Normally we'll find it in the stratosphere, where it protects us from the sun's rays, UV rays. It can also be used to purify water. That's just a side, like extra information. Okay, halogens. Those can also be used to replace oxygen. They're very corrosive, so we have to be careful when we use them. And because they can burn, well, they can attack or damage your respiratory system. So again, you have to be careful, or one has to be careful when they use halogens as an oxidizer. So that is it for us today. I shall see you for your next episode in a few days. Goodbye.